Okay, sir. Uh, Dear friends, very good morning and warm welcome to all. Thank you for joining us for today's international webinar. I want to offer my thanks to our Hindustan management, our CEO sir, Dr. K. Karnagaran sir, advisor sir, Dr. Anna Thurai, and the Hindustan Group of Institution and Dean of Academics, and our HODs, Dr. K. Muthukumaran sir, Professor of Chemistry, and Dr. K.P. Uma, Professor of Mathematics, and our faculty colleagues for their encouragement to conduct this webinar. I offer my thanks to our chief guest for accepting our invitation to direct this webinar. Today, we are presenting carbon-based nanocomposites, their applications, with special references to biomedical applications by Dr. Y. Dominic Ravichandran, sir, Professor of Chemistry at Volga University, Ethiopia. And did his postdoctoral studies at National Taiwan University, Taiwan, and Pokyang National University, Busan, South Korea. He has around 50 publications in peer-reviewed journals, and he's also worked in the editorial board for many journals. And he's outstanding reviewer on the Elsevier journal. And he served in academic career. Dominic sir worked as a former professor of chemistry at VIT University, Vellore, and worked as a dean at Karpam College of Engineering, Coimbatore. Now, I request our today's chief guest to deliver his presentation. Friends, if you have any questions during the presentation, please type them into the chat box. I'll bring them up during the presentation, and we will also have time for question at the end. Thank you, sir. Thank you, Professor.
Sir, welcome to our Mr. H.O.A. Sir, please.
Sir, is it audible?
Yes, sir.
Hello.
Sir, is it audible?
Hello.
Sir. Yes, sir, audible.
Audible?
Please.
Okay. Good morning to everyone. It's a great honor for me to introduce our well-known, renowned scientist, Dr. Y. Dominic Ravichandran, now Professor of Organic Chemistry at Volga University, Ethiopia.
Hello, can I start?
First, are you able to hear? Hello? Now can I proceed? Hello?
Yes, sir, you can proceed, sir.
Okay.
Sir, please wait.
I wish to inform that this gathering, that professor is my long-time friend. We met each other in our whole life 4 times, and you may surprised to see on different occasions. I don't know the professor is remembering or not. Initially I met him in REC Trichy when he was doing research, and again we met at Vellore when I was in Tandepariyar Government Engineering College, and again at GCT when he came for another meeting. And one more time I met in KIT for his candidate when he was the dean in Karpagam Institute of Technology. I'm really happy indeed in welcoming him, and I will again briefly tell his resume. Dr. Y. Dominic Ravichandran is the Professor of Organic Chemistry in Volga University, Ethiopia. After obtaining his PhD in Chemistry at REC Trichy, Bharathidasan University, he did his postdoctoral studies at Taiwan University, which is again a reputed university in Taiwan, and working as research professor at Marine Bioprocess Research Center, Busan, Republic of Korea. So, in his life, he has visited across all the countries. He rose through the ranks and served as a professor in Vellore Institute of Technology, Vellore, where he brought many innovation and he got several funded projects there. And from there, he visited once to our Coimbatore GCT. And then he moved to Karpagam College of Engineering and served for as a dean for some time and before moving to our present institute. And he is a very well impacted papers in all the journals and in his credit he is having 50 papers in his treasury, and also he is not only a very big shot in organic chemistry. He started working in NANOCOMPOSITES and he has visited many countries on invitation, including German, South Korea, and Taiwan. And he is honored by Elsevier for his outstanding contribution in reviewing. He is also editorial board in many leading journals, including Journal of Pharmacy and Drug. Now, he is also serving as director of Star Journal of Olega University. In this great day, may, on behalf of all our friends, may I request our Honorable Professor Dr. Dominic Ravichandran to share his rich idea on the carbon nano composites, mainly with respect to the biomedical application, which is the need of the hour in this COVID-19. And before handing over the mic to him, I really appreciate each and every effort done by Professor Ganapati Raban, Professor Prabhu, Professor Prabhakaran, and Professor Dr. Balamurali, and of course my young student Sriram and all other my colleagues. I hand over the mic to our Professor Dr. Dominic Ravichandran. Thank you so much.
So you can start now, sir. Dominic, sir. Welcome, sir. So you can start now, sir.
Professor, thank you for your nice words and introduction. I thank the management of Hindustan institutions and the organizers of this webinar for taking all the pain in organizing this webinar. And Is it clear? Hello? Uh, is it clear now? The slides are clear? Now? What about now? Now is it visible? Just a minute. Is it clear now? Hello? Can I proceed? Very good morning and welcome to the presentation on carbon-based nanocomposites and their application with a special reference to biomedical application and overview. In this, we will be focusing on composite materials, nanocomposite materials, carbon-based nanocomposites, general applications of composites, and some biomedical applications of composites. To start with, on composite materials also referred to as composite materials or simply composites are material formed by combination of two or more materials with different properties to produce an end material with unique characteristic. The two materials that we combine work together to give the composite a unique property. However, within the composite, you can easily tell the different materials apart as they do not dissolve or blend into each other as in an alloy. Coming to the types of materials, the types of material composites can vary based on the matrix, whether it is a metal or an inorganic compound or a polymer matrix, or whether it is a ceramic or a carbon. Based on the matrix, we call it as the corresponding composites. And we can also vary the reinforcing material like glass fiber, polyethylene fiber, carbon fiber, aramids, and so on. And these composites can also be classified into thermosets and thermoplastics. Thermosets are non-remoldable plastics. Some of the examples are the carbon epoxies, carbon bismalonide, and so on. And thermoplastics, we can see some examples like carbon polyether ether ketone, and so on. When we come on to the nanocomposites are a broad range of material consisting of two or more, of which at least one should be of the dimension of a nanoparticle or nanomaterial, where it should be between 1 to 100 nanometer. And we have different types of nanomaterials. It can be classified as 0 dimension, 1 dimension, 2-dimension and 3-dimension. Some of the examples are given here, where when it is a 0-dimension, it could be a fullerene, onion-like carbon, carbon dot, or a nano diamond or a graphene dot. When it comes one-dimensional, it can be a carbon nanotube or a multi-walled carbon nanotube, or it can be a carbon nanohorn. And when it comes to 2D, it can be a graphene sheet or a carbon nanoribbon or nanofiber. And when it comes to the 3D, we can have graphites where the graphenes are arranged or staked one over the other. And these materials are in the range of 1 to 100 nanometers. And so we call these our nanomaterials. And so we use it, when we use it in the composite, we call it as nanocomposite materials. And when we come on to carbon-based nanocomposites, the question is why we need carbon nanostructured materials. The carbon-based nanomaterials have very good strength and many unique properties, and these materials are making these carbon nanostructured materials unique. Some of the carbon-based materials are graphite, graphene, graphene oxide, the oxidized form of graphene, nanodiamond, a bulky ball, and fullerene, a multi-watt carbon nanotube, where the graphene, that is multiple layers of graphenes, are rolled to give a cylinder-like structure, a single-wall carbon nanotube, where a single graphene sheet is rolled to give a cylinder-like structure. And these are some of the examples, like carbon nanohorns, where it is like a horn, and you also see that these horns are in nano size, and so we call it as nanohorns. And because it's made of carbon, we call it as carbon nanohorns. Timeline of carbon-based nanomaterials. The nanodiamonds was introduced in 1983, and many researchers started working on nanodiamonds. And in 1985, fullerene came into the field, and many people started working on fullerenes. And it continued. And in 91, 93, the multi-walled and single-walled carbon nanotubes started coming in to the research field, where people started using it, and people started exploring these materials. And in 99 and 2000, we started having nanohorns and nanocones. And in 2004 and 2006, the graphene started coming in. And from then on, people started using graphene as a very important material in case of composites and many other material. And now graphene is finding its place as a very important one in material science. Various methods for preparation of nanocarbons. We use different methods, starting from arc discharge method, laser ablation, carbon vapor deposition, and Hammer's method. These are very common methods used for the production of nanocarbons. Looking at the different techniques, carbon discharge chemical vaporization and laser ablation. In arc discharge, we have two graphite rods, and these rods are kept around 1 millimeter to 2 millimeter apart and connected to 100 amps. When it is with a distance of 1 to 2 millimeter, what we get is a carbon quantum dot or fullerene. But when it is increased from 2 to 25 millimeter, we get the other materials like the CNTs, carbon nanotubes. And in case of laser ablation, we use what is called as a laser pulse, which is used to blast the graphite, and it produces nanotubes and mainly used for producing single wall nanotubes. And this is producing primarily the single wall nanotubes with large diameter range and a high purity. Comparing these three, the laser ablation is expensive and is used for producing high quality single wall carbon nanotubes. And in case of arc discharge, the purity is less and we have to purify before use. And coming on to chemical vapor deposition, the substrate is kept in an oven and heated at 600 degrees centigrade and slowly added carbon bearing gas such as methane. As the gas decomposes, it frees up the carbon atom, which recombine in the form of nanotubes. Looking at the yield, the arc discharge method gives you a yield of 30 to 90%. In case of chemical vapor deposition, it's going to be 20 to 100%. And in case of laser ablation method, it is greater or equal to 70%. And coming to the defects, the arc discharge method needs a lot of purification and is so not a preferred technique. And laser ablation is not very often used because of its cost, which is very expensive. And very commonly used method is the chemical vapor deposition method. The trends on publication of carbon-based nanocomposites. If you look at the publication side, till 2012, the publication were concentrated on carbon nanotubes. And from 2013, people started working on graphene and graphene oxide. And we started the publication to grow year on year. And in 2018, we see most of the papers come from graphene and graphene oxide, and it goes on increasing. Carbon quantum dots. Since the discovery of carbon quantum dots, which is a crystalline form of carbon, a large variety of techniques for the preparation of carbon quantum dots have been developed, and many people have reported these techniques. Generally, the synthetic method of carbon quantum dots can be classified into two groups: the top down and bottom up method. In the top down process, the macromolecule is destroyed or dispersed into small sized carbon quantum dots. And in case of bottom up approach, it mainly refers to the polymerization of a series of small molecules into carbon quantum dots through chemical reaction. Here we see some examples of top-down process like arc discharge, laser ablation, acidic oxidation, And some examples for bottom-up process are combustion routes, microwave pyrolysis, hydrothermal synthesis, and electrochemical method. In case of nanocarbon tubes, we use arc discharge, laser ablation, chemical hydrothermal method, chemical vaporization method, and which is normally referred as CVD. Under CVD, we have plasma enhanced, thermal, radio frequency, microwave plasma, oxygen assisted, water assisted, hot filament, and so on. When we take these carbon materials have the problem in solubility, and they are not dispersed even in case of organic and aqueous solvents. And this creates a lot of problems. In case of biomedical application, sometimes these material are accumulated in the body, and the bioaccumulation is sometimes taken as a toxic material, and it is not good for the application side. And in order to overcome that, people go in for functionalization, where you attach some protein or organic moieties, and these moieties disperse these molecules well into and improve the solubility so that these are solubilized. And looking at the functionalization, we have edge functionalizations, where it is going to be, that is, the molecules are connected at the edge, and if they are connected at the edge, it is called as edge functionalization. And if the molecules are going to be connected at the base, it is called basal. And if it is going to be connected by a covalent bond, it is called covalent functionalization. And if the nanotube is going to be connected to the organic molecules by binding, and if it is going to be attached to the surface by a van der Waals or electrostatic force of attraction, you call it as non-covalent functionalization. And the endohedral fillings are the fillings of the organic molecules or other molecules inside the carbon nanotubes, for which the molecules should be of small size. When we come to the functionalization of multi-watt carbon nanotubes, it can be done by oxidation, where the multi-watt carbon nanotubes, where the graphenes are rolled, the multi-layered graphenes are rolled, so you have too many layers of graphenes, and it can be functionalized using mixture of acids like sulfuric acid and nitric acid in a ratio of 3:1 and sonicated for 20 minutes, after which it is reflexed for 3 hours to get the functionalized multi-walled carbon nanotubes. In case of the functionalized multi-walled carbon nanotubes, we see the carboxylic acid groups are attached to the layer by a covalent bond. And coming on to the composite formation, in case of the functionalized multi-walled carbon nanotubes, the multi-walled carbon nanotubes can be attached to polysaccharides or any material for that matter, which can be connected to this carboxylic acid. And our interest was on polysaccharides to be added. So we have used polysaccharides with these functionalized multi-carbon nanotubes. And in water medium, it was stirred for 3 hours, where the polysaccharides gets attached to the multi-wall carbon nanotubes through the functionalization. And this is further added with HAP, that is hydroxyapatite, a very well-known ceramic material, and stirred for 24 hours in water medium. And this results in a composite, and we create the scaffold of this by freeze drying method, where these composites are frozen at minus 80 degrees centigrade and lyophilized to get these things. And these composites can be molded into different size based on your requirement. We also perform thermogrammetric analysis of composites to see the thermal stability of the material. And we see that from 30 to 130 degrees, there is some water loss, and from 202 to 660 degrees centigrade, there is removal of organic portion, and beyond which it is very stable. Coming to graphene, graphene, as I told you, is a very popular and a material which is gaining importance in recent time. And it has different application like conductive ink to chemical sensors, light emitting devices, composites, energy devices, touch panels, and high frequency electronics. And its unique electronic, mechanical, optical, thermal, and chemical properties have made it most sought after in nanomaterial science. And graphene can also be synthesized by the 2 different methods that we referred earlier, like top-down and bottom-up. In case of top-down, you have a mechanical exfoliation, chemical exfoliation or chemical synthesis. And in case of bottom-up, we have pyrolysis, epitaxial growth, CVD, and others. The different forms of graphenes that we have are graphene, indicated by A, graphene oxide. When you oxidize these graphene, what you get is graphene oxide, which is indicated by B, where you see oxygens around. And C is a reduced form of graphene oxide, where we can reduce this graphene oxide using a reducing agent like sodium borohydride, and this will give the reduced form. If not, it removes all the oxygen, it removes most of the oxygen to give the required functionalities. And we also see what is called as a porous graphene, which is indicated by D. And in case of porous graphene, there are pores, and these pores are very important in some applications. And E is a crystal form where it is going to be called as graphene quantum dot, and the F is a SEM picture of the graphene. And this is again to indicate the difference between the graphite and graphene. Graphite is one where the graphenes are staked one over the other and are held together by van der Waals interaction or electrostatic forces. And if you look at the graphene oxide and reduced graphene oxides, the oxygen moiety in graphene oxide is more, and in case of the reduced graphene oxide, the oxygen moieties are reduced. And different functionalization of graphene. Graphene has, again, as we are seen in case of CNT, different functionalization. And if it is done on the edge, it is called edge functionalization. And if it is done on the surface, it is called as basal plane functionalization. And if it is adsorbed onto the surface by adsorption process, then it is called non-covalent adsorption on the basal plane. And we can also have asymmetric functionalization, where we can have different groups attached to different sites. And we can also have the self-assembly of graphene, where the graphenes are assembled one over the other and connected by the groups. And when a graphene is connected to the organic molecule by a covalent bond, it is called covalent functionalization. And if it is blended onto the graphene, like what you see, a polymer blending onto the graphene, it is called as polymer blending. And if the attachment is done by electrostatic interaction, it is called as electrostatic interaction. And in case of aromatic compounds where you have conjugated systems, the rings are held together by what is called as pi-pi interaction. And in those cases, it is called functionalization by pi-pi interactions. The pi-pi staking interaction as a kind of attractive and non-destructive, non-covalent interaction have been widely explored for the application of modern chemistry and molecular biology, supramolecular armamentarium, among which bio applications have attracted tremendous attention due to unique advantage, such as strong binding force, non-destructive fabrication process, and simple operations. And one application to mention here is these pi-pi staking is a very important property and process by which the cancer therapy is going on with the functionalized graphenes. To prepare something like a pi-pi staking, we start with graphene and aniline trimer taken in equimolar ratio, mixed in a solvent like dimethyl acetate, and it is sonicated for 1 hour, where it disperses the graphene and the aniline trimer is getting itself adsorbed by the pi-pi interaction onto the graphene sheets. Once this is done, we add what is called as pyrometallic dianhydride and oxydianiline, where it is called 4,4-oxydianiline. Mix these to this mixture and kept at the stirring for 24 hours in the nitrogen atmosphere to get what is called as polyamic acid graphene composite or polyimide chain graphene composite. And once we get this graphene composites, it can be casted onto a glass plate of 2 centimeter to 2 centimeter size and air dried under nitrogen atmosphere so that we get the sheets of composites. Here you can visualize how the functionalization is going to disperse the graphene into the medium. The first one, that is A, is the graphene in a solvent of dimethyl acetate. When you add graphene to dimethyl acetate, it settles down and it is not getting dispersed. But when it is attached with aniline trimer, you see that the graphene is dispersed the same way when you have a PAA graphene composite in solvent like dimethyl acetate, it gets dispersed. And these properties, that is the solubilizing property and also the attachment of these organic moiety, help in modifying these graphenes and tailor make the graphene to our need. Coming to the characterization part of the composites, we normally use different techniques. To mention few, I have taken a very common technique, which is UV visible, and the Raman, which is very commonly used in case of these carbon nanomaterials. The figure indicates two different things. One, A, which is your UV spectra, and B is your Raman. And in case of your A, we have the black line indicating the UV spectrum of aniline trimer, where you have two adsorption peaks, one at 336 nanometer and the other at 582. And when it is forming the composite, it again gives two peaks, but the absorption peaks are at 328 and 582. When we go on to the Raman spectrum, the graphene has two bands, that is 1582 called as your G band, which is specific for graphene, and the D band, which is for the deviations which you have some disturbance in the graphene, which is going to be at the D band of 1336. And you also see that the composites have additional peaks in the Raman spectrum. In the UV visible spectroscopy of aniline trimer and aniline trimer graphene in dimethyl acetate, the aniline trimer exhibited two characteristic peaks at 336 and 582 nanometer, which are associated with the benzenoid and quinoid absorption peaks, 336 for the benzenoid and 582 for the quinoid absorption peak. Similarly, when you record the spectrum for the aniline trimer graphene suspension, it also exhibited two absorption peaks, whereas the peak for the pi-pi transition of the benzenoid was blue shifted from 336 to 328, which I've indicated in the graph. And this confirms the pi-pi interaction between the aniline trimer molecule and the graphene. In case of the Raman spectroscopy, for the Raman spectra of graphene, aniline trimer graphene, graphene exhibits a typical G band at 1582 centimeter minus 1, which is a special peak for graphene, and D band at 1336. And in case of pure graphene, it will not have the D band. And in most of the cases, because of some disturbance in the graphene structure, you'll have a D band at 1336 centimeter minus 1. And the ratio between this G and D band will indicate the type of distributions and disturbance that you have in the graphene sheets. On the other hand, the aniline trimer exhibit a CN stretching at 1346 centimeter minus 1, phenazine adsorption at 1499 centimeter minus 1, and so on. And it is apparent that the G band of graphene is getting shifted from 1582 centimeter minus 1 to 1580 centimeter minus 1, and the D band shifted from 1334 centimeter minus 1, 1336 to 1334 centimeter minus 1, indicating a charge transfer interaction between graphene and AT because of the pipe-wise sticking. And few applications of carbon-based nanocomposites. If you look at the slide, you find the materials made of carbon nanocomposites, like your automobile industry, which make car, bus, and so on. Your personal articles, including helmets. Sports articles like golf stick, tennis bats. You also see some drones, fighter aircrafts, aeroplanes, submarines, ships. You also see some radars, and in case of your PVs, where the carbon nanotubes are finding applications today. And also you see the spacecrafts and the satellites. In all these cases, you use the carbon nanotube composites as a very good material. Coming to the application of carbon-based nanocomposites in automobile industries, nanomaterials are used in fuel cells and in batteries. Nanofilms for self-cleaning. It is also used as heat shielding, polymer glazing, and it is used as nano-inclusion in lubricant. The nanocomposites are used for coating. Nanoparticles are used in tire materials, and the catalyst of the carbon nanotubes or carbon nanomaterials are used in the reactor. And you see the sensors and other material, other parts of the cars are made by the composites, which are very common. Here we see a CNT steel composite, reinforced structural supercapacitor, and this gives a high strength material for your cars. And recently people started using these type of materials for the car because these materials are light in weight and will give strength better than that of normal thick steel. In case of aerospace industry, even F-35, the carbon fiber composite is used where it finds 35% of the structure in the fighter plane F-35 being a carbon composite. The carbon composites used in these fighters are kept as confidential because it is patented and kept, so they don't reveal what is the composition they use, but they say that 35% of these are used by composites. And in case of Airbus A380, again, the wings and other parts are made by carbon-based composites. The carbon nanotubes, along with conducting polymers, are finding many applications as a carbon-based composite. Some of them are like supercapacitors, sensors, OLEDs, solar cells, electromagnetic absorbers, and advanced nanoelectronic devices. The conducting polymers commonly are classified as conjugated polymers, which consist of alternating single and double bond along its linear chain of sp2 hybridized structure. The conductivity of the conducting polymers rely on these double bonds, which are sensitive to physical and chemical interaction. And these pi electrons are very important for the conductivity. Similarly, in case of CNT also, we have sp2 hybridized bonds over the structure, and the CNT possesses unique structure which is mechanically strong and flexible, and it exhibits extraordinary electrical, optical, chemical, and mechanical property when it is used along with conducting polymers as a complementary material. Some of the conducting polymers that are employed are polyaniline, polypyrrole, polygraphene, and we also have other recently developed conducting polymers which are finding applications in our solar PVs and so on. And CNT-CP, that is conducting polymer composites for nano devices, the CNT have a very long mean free path, ultra high carrier mobility, and can be either very good conductor or a narrow band gap semiconductor depending on the chirality and diameter. Mixing up together both material, that is the carbon nanotubes and the conducting polymer, is going to give a composite with a strong interfacial coupling via donor-acceptor binding and pi-pi interactions. The coupling of the carbon nanotube and conducting polymer in a composite has been found to affect their chemical and electronic structure. Beyond a simple combination of their properties will be synergistic in effect, and new features appear and can develop into many applications. In case of photovoltaic cells, you can see whether it is the first generation, second generation, or third generation, the carbon nanocomposites are finding immense use. And some other applications that we see is the OLEDs, which is getting prominent, and the organic light emitting diodes, which will be replacing our conventional LEDs and make these LEDs to be machinable and flexible, making this useful in producing many nano devices. You also have flexible electronics, wherein the material, the composites are flexible with improved properties, and this is gaining importance, and we will be seeing a lot of these material in our devices in coming years. To mention few, to have a rolling mobile where you can just roll it and put it on a packet, or you can have a tab which can be rolled and kept in your bag, and so on. Coming to the fabrication, there are different fabrication techniques. The one which I used and indicated is called as deep freezing or technique. And the other technique is 3D printing, which is very common and used very widely in composites. You can see the cycle which is printed by the 3D printing from the composite as one single component, and even very complex structures can be made with this 3D printing using your CAD computer-aided designs, and with that computer-aided design, you can print any structure layer by layer to get the required structures. And this is also finding application in biomedical applications, wherein you fabricate different organs using these scuffles by this 3D printing. To sum up some of the applications that we have seen in graphene, the graphene-based composites are very useful in automobile and airplane components, in LED lighting, chemicals, conductive ink in EMI screening, high-speed transistors, flexible display touch panels, solar cell battery, and supercapacitors. Now coming to biomedical applications of nanocomposites. The polymer nanocomposites are very commonly used as scaffold for tissue engineering, medical implant, drug release, gene delivery, biosensor, bioimaging, dental applications, and wound healing. I will not be touching all these applications because of time constraints. I'll be taking few examples to explain how these are used, and I'll be focusing on the graphene and carbon nanotubes and some application in tissue engineering like bone tissue engineering in my presentation. And these are some of the applications that we have, like invasive surgery, biosensors, very commonly seen the glucometers, where the strips are made of the composites, MRIs, where you have the components made of composites, and you also, as I told you, the pi streaking is used in case of cancer therapy and drug gene delivery. So these are some of the modification of the composites, where you have wearable devices, you have the optoelectronics, which gives you a very thin sheet of composites with the required properties. It is pasted on the hand, where you can measure the temperature, and you can also measure your pulse and so on. And we can see other applications as we go on. And some potential application of nanocomposite in orthopedics is getting importance, because when we have some bone defects, when you go in for the surgery, normally people use the metal implants, and the problem with the metal implant is that the metal implant is not going to be biocompatible. And if you want to make those things biocompatible, you have to go in for what is called as a coating of these composites. And if you use these metal implants, you also go for what is called as secondary surgery to remove the implant after some time. Otherwise, it is going to give you some pain and other complications on time. And in order to avoid that, the recent development is to have a scaffold and to use the scaffold for the treatment of your bony defects. What are the available treatments for bony defects? Bone grafts or metal implants are currently used for bone defects. We have two different grafting. One is called autograft from the other part of the body of the same human, and allograft is from other donors, or considered to be ideal procedure for bone grafting. And in these treatments, it has limitations in donor sites, and additional surgery and unwanted disease transmissions are seen. And in case of metal implants, the metal implants have disadvantages like undegradation after implantation, required secondary surgery, stress rises in existing bone, and may release toxic ions which causes infection. Coming to tissue engineering provide a new path towards bony defect which offer an excellent alternate for the existing treatment. Bone tissue engineering is a multifarious and dynamic process that initiates with migration and recruitment of osteoprogenitor cells, followed by their proliferation, differentiation, matrix formation, along with remodeling of the bone. Scaffolds are artificial matrices designed not only to mimic the biological property of the tissue matrix, but also to improve the mechanical strength of the bone. It will provide the 3D spaces for cells to undergo proliferation, differentiation, and act as carriers to transfer cell and bioactive materials to defect sites. And what are the requirements for bone engineering is that it should have an extracellular matrix, like what you see in this picture. The connective tissues of the interstitial matrix, and only to mimic this, we have selected what is called as the polysaccharides. And some of the polysaccharides which we have seen are asparine, keratin sulfate, condyte sulfate, hyaluronic acid, and the extracellular matrix, intracellular communication, cell matrix interactions, growth factors, 3D structures, adequate mechanical strength, biocompatibility, osteoconductivity, porosity, where we expect the porosity to be greater than or equal to 90%, interconnected pores for the tissues to develop, and finally, the biodegradability to reduce the toxic effects. The need for hydroxyapatite. Hydroxyapatite is used as a replacement for the broken bone because of its biocompatibility, bioactivity, osteoconductivity, and similar structure to the inorganic component present in the bone. However, the poor mechanical strength and brittleness of the HAP make it unfit for major load-bearing applications. And because of these limitations, that we use other materials like the polysaccharides, which is going to bind the HAP, and the carbon nanomaterial, which is going to use as a material for the composite to increase the mechanical strength and other properties. HAP can be synthesized in the laboratory, or it can also be chemically prepared in the laboratories, or it can be isolated from natural sources. In our cases, we have functionalized the multi-walled carbon nanotubes by oxidation as indicated earlier. The multi-walled carbon nanotubes are functionalized by oxidation using acidic mixture in the ratio of 3:1, and the conditions are indicated as discussed earlier to give the corresponding functionalized multi-walled carbon nanotube. And the scaffolds are prepared like this, that is, to the functionalized multi-walled carbon nanotube, the polysaccharides are added, and it is stirred for 3 hours, mixed with hydroxyapatite, and once you have a suspension of these composites, as I told you, there are definite techniques like your 3D printing, your freeze drying method, and other recent techniques that we have. to create these type of composite scaffolds. One such method is the freeze drying, and which we normally employ because of the availability of the material. And in this case, we freeze the suspension at minus 80 degree in a particular mold so that it solidifies and lyophilized and dried so as to get the composite scaffolds. The composite scaffolds prepared are shown in your picture in the photograph. You can see how it looked like. And in the characterization part, we use the XRD analysis where we record the XRD of which is giving a peak at 1934 for that of the polysaccharide. And we also record that of the functionalized multivart carbon nanotubes, which will be seen at 26.05, and the HAP and the composites. And crystalline, it is amorphous in nature, and HAP is crystalline. The functionalized multivart carbon nanotubes and gallium to be predominant
Sriram, any problem? Network problem? Huh? Sriram?
No, sir. I thought problem in Ethiopia.
Okay, sir. என்ன பண்ணலாம் ஸ்ரீராம்? வெயிட் பண்ணலாம். ஆமாப்பா, கொஞ்சம் வெயிட் பண்ணலாம். ஒரு 2 மினிட்ஸ் பார்ப்போம். அவசரப்பட வேணாம். தேங்க்யூ.
ப்ரொஃபஸர் நான் அவருக்கு கால் பண்ணேன், பட் ஐ கான்ட் கனெக்ட். சம் நெட். ஸோ 2 மினிட்ஸ் வெயிட் பண்ணலாம். பண்ணிட்டு ஸோ you can proceed, Professor.
Okay, sir. Please inform me. Okay, sir. You just inform me.
Okay, sir.
Okay. The vote of thanks. Thank you, Professor. ஸ்ரீராம் பேசிடலாமா? வாட் ஆஃப் சரி பேசிடுங்க, பேசிட்டு சொல்லுங்க. இல்ல அவரு எத்தியோப்பியால இருந்து பேசுறாரு, ஸ்பீக்கர் ஆப்பிரிக்கால இருந்து பேசிட்டு அவரு வெளியே போயிட்டார், கனெக்ஷன்.
ஹலோ சார்.
சொல்லுங்க ஸ்ரீராம். ப்ரோ சார் நான் பேசிட்டேன்.
கணபதி
சொல்லுங்க ப்ரோ சார். ப்ரோ சார் கேக்குது எனக்கு.
பேசுறேங்க சார், கண்ட்ரோல் பண்ணிருக்கேன், பின்னாடி பேசுறேன்.
ஓகே ப்ரோ சார், தேங்க்யூ ப்ரொஃபசர். I heartily thanks to our chief guest, scientist Dr. YD.
You can.
Shall I continue?
Professor, you can proceed, Professor.
Okay, thank you, Professor. Okay, I heartily thanks to our chief guest, scientist Dr. Y. Dominic Ravichandran sir. Thank you for your valuable presence on today's session on carbon-based nanocomposite, their applications with special reference to biomedical applications. Thank you, sir. And we thank to our management and our CEO, Dr. K. Karnagaran sir, advisor, Mr. Annadurai sir, Dr. Annadurai sir, Dean of Academics, HODs, our Dr. K. Muthukumaran sir, KP Uma madam, Professor of Mathematics, and our faculty members and friends. And special thanks to our students, student coordinator, Mr. Sriram. Once again, I thank you all. Thank you, sir. Thank you, Professor Ganapati Raman, sir. The session is over.